Welcome to this lecture on transition metal organometallic chemistry from principles to applications. We have been discussing a very important topic in the last few lectures, and this is about transition metal alkyne complexes. In this regard, we have looked into various aspects of these special types of compounds, which are right from the synthesis as well as their characterization as well as their reactivity. Now, one important aspect which emerges from our discussion on transition metal alkyne complexes is that these are very important compounds, not only from the fact that they stabilize many alkynes which otherwise are difficult to stabilize in the free state. For example, cyclohexane or benzene or benzidine, which are extremely unstable molecules by themselves, but when they are coordinated to transition metals and make the transition metal alkyne complexes, these unstable alkynes are stabilized. We have also seen that these transition metal alkyne complexes also stabilize not only unstable alkynes which we just spoke about, but also alkynes which are extremely reactive and explosive, particularly the haloacetylenes, which by themselves in the free state are extremely reactive, are stabilized when upon coordination to transition metal. What we come to see is that these transition metal alkyne complexes are extremely interesting type of organometallic compounds. We have as far as the reactivity of these interesting compounds are concerned, what we had seen that they show diverse range of reactivity. For example, transition metal eta 2 alkyne can be converted to eta 3 allyl complexes. So, one can see that eta 2 alkyne can be converted to eta 3 allyl complexes by a series of rearrangements that we had seen. We had also seen that in presence of transition metals and alkynes, several kinds of dimerization, trimerization as well as cycloorganization reaction take place, and these have been achieved by kinetically labile organocobalt or organopalladium complexes. So, this all of this has been discussed in the last lecture, where we looked at various kinds of useful reactivity that are seen for these transition metal alkyne complexes. So, with that in the background, we are going to take up some more interesting reactions of transition metal alkyne complexes in this lecture that we are going to talk about and discuss today. So, one such interesting reaction is this cobalt catalyzed cyclization of alkynes. Now, this is an interesting reaction where acetylene of in the terminal chain ends, terminal acetylenes N equals 2 to 5 in presence of another alkyne and catalyzed by this cobalt carbonyl complex, gives this cyclic compound and where the cyclization has been achieved between this alkyne and these two terminal acetylene and this R1 CR2 or this alkyne to give this homocyclic compound. So, this synthesis of homocyclic systems. And these are reactions which are very specific to organo-cobalt reagents. So, cobalt is acting as a catalyst to carry out this kind of 2+2+2 cyclization reactions generating aromatic rings. So, this is a very nice demonstration of reactivity of transition metal alkyne complexes as is observed. This is sort of related to the oligomerization dimerization reactions that we had seen, we have discussed in the earlier lecture, and here we see that instead of its oligomerization or dimerization or trimerization of the same acetylic unit, over here what we see is cyclization of two different acetyl unit resulting in these homocyclic systems. So, another example of a very famous example of cobalt catalyzed cyclization of alkynes and nitriles, and this is an important reaction because this cyclization leads to the formation of pyridines, which are useful value added chemicals to give pyridine, and the reaction is between two acetylene reacting with RCN in presence of the cobalt CO cord to give this pyridine moiety, substituted pyridine, and this is a named reaction. This is called Bonnemann reaction and has been developed by Bonnemann in 1974 and has been successfully used for preparation of pyridine or substituted pyridine. So, here is another example where we see that cyclizations of the C triple bond C as well as C triple bond N results successfully performed with Cp cobalt cord catalyst, giving rise to this pyridine, where this nitrogen comes, nitrogen Cr comes from the nitrile, substituted nitrile, and these two comes from the 2-acetylenic moiety. Now, let us take a look at the mechanism for this Bonnemann cyclization in bit more detail. Mechanism for Bonnemann cyclization. So, Cp cobalt CH reacts with another molecule. So, we have a cobalt complex of acetylene reacts with another molecule of acetylene. So, this is the active species where cord of the Cp cobalt has been replaced by an acetylenic moiety, and then the second acetylene comes in to give this Cp cobalt diacetylenic compound which again reacts with nitrile CN to give a metallocyclopentadiene intermediate of the type shown. So, this intermediate is formed by cyclization of these two acetylenic unit to give this cobalt metallocyclopentadiene, and then this nitrile is coordinated to cobalt. From this intermediate, this nitrile inserts into the ring, eliminating this pyridine, substituted pyridine as shown here, and giving back Cp cobalt as the intermediate. Now, Cp cobalt can take up another molecule of acetylene to give this acetylenic compound. Now, this Cp cobalt can be generated from CpCoL2 by loss of 2L2, or in presence of 2L2 it will give that. L2 is diolefin. So, this clearly states a very nice catalytic cycle, whereby the cyclization of two acetylenes and nitrile results in the formation of much value added substituted pyridine, but it goes through metallocyclopentadiene intermediate containing cobalt in the metallocyclopentadiene ring scaffold. So, this is a very nice demonstration and a utility value added reaction of transition metal alkyne complexes, thereby highlighting why these are so important class of organometallic compound. Now, we have seen examples of dimerization, trimerization, as well as we have seen cyclization of various alkynes. So, the next example that we are going to talk about is tetramerization of acetylenes to give cyclooctatetraene derivatives by nickel complexes. So, this reaction of acetylene to give cyclooctatetraene derivatives. So, the reaction can be given by 4 molecules of acetylene in presence of nickel cyanide and CaC2THF 80 to 120 degree centigrade 15 bar of pressure gives this cyclooctatetraene in 70% yield. And what has been found that labile nickel 2 complexes like nickel ACAC whole 2 or nickel CN2 are best catalyst. And for these particular reactions, and these are used in industrial production by BASF. So, here we see a real practical utility of this tetramerization reaction, giving cycloocta tetra in derivative by reacting acetylene with nickel cyanide. So, there are other useful reactions of acetylene, particularly the cyclooligomerization with incorporation of carbon monoxide molecule. This is also another interesting reaction. Cyclooligomerization of alkynes with incorporation of carbon monoxide molecule, and the best example of this is FeCO5 reacting with RCCr. When R equals H gives this C double bond O. So, this is a 5-membered ring containing the CO, and this CO has got inserted from the iron carbonyl. So, we see this cycle 5-membered ring with ketones, cyclopentenones coordinated to iron tricarbonyl. Now, when R equals pH, then one gets these cyclobutadiene complex as shown. When R equals methyl then one sees benzoquinone kind of compound. Here the carbonyl got inserted from FeCO3 from iron pentacarbonyl, 2 of the COs got inserted, and also the other product when R equals H is the 7-membered ring containing carbonyl, and here also FeCO3. So, what is being prominent over here, that the cycloorganization gives a versatile range of products, some containing the carbon monoxide incorporated in the cyclooligomerization reaction, and in case of phenyl it does not. But what is to be stressed out over here, that a wide versatility of the cycloorganization products were obtained by the cyclomerization of acetylenes with the incorporation of CO molecules when the acetylene is reacted with iron pentacarbonyl, and depending on the substituents of the alkyne, large number of different products can be obtained, and this shows how versatile this cyclooligomerization reaction is, towards producing various kinds of important compound. Another important reaction in this context is the formation of ferrole ring, where iron itself is part of the 5-membered ring. So, formation of ferrole ring C4 H4 FeCO3. So, iron CO3 is part of the ferrole ring, and one can see interesting bonding. We will look at the bonding after we see the reaction. FeCO5 plus HC CH to give FeCO3 FeCO3, which can be in equilibrium with the other center, FeCO3 FeCO3, and these have been structurally characterized. So, one has full metrical data for it. So, this bond is 139 picometer, this 142 picometer, and this is 249 picometer. So, what is evident from here is that this FeCO3 is linked by metal-metal bond, which is kind of extremely interesting. And in this dimeric complex, this C4 H4 FeCO3 unit is pi bonded to another FeCO3 unit. So, this is an interesting reaction what we have seen, where this ferrole ring is formed by reaction of FeCO5 with acetylenes. Alkynes also acts as a 4 electron donors, particularly in this reaction with cobalt carbonyl. Dicobalt CO8 plus gives this complex where acetylene is acting as a 4 electron donor, cobalt CO3, there is a cobalt bond, and this is 146 picometer and 247 picometer, and alkyne can act as bridging ligand towards two metal centers. An example of this is seen over here, as well as in this reaction, where the reaction of Cp Ni CO dimer reacts with R C R eliminates 2 molecules of CO to give this compound where alkyne is attached to the 2 metal center okay, and this eliminates 2 CO. So, these alkynes acting as a bridging between 2 center, and with this maybe one more reaction which is of interest is Pauson-Khand reaction, and this reaction is between this norbornene strained olefin plus acetylene plus carbon monoxide and 10% of cobalt 2 CO8 60 to 70 degrees centigrade gives this tricyclic compound which has a CO, and this is example of 2 plus 2 plus 1 cycloaddition of an alkene, alkyne and CO, alkyne, alkene and CO in presence of dicobalt octacarbonyl to give cyclopentanones. So, with that let me summarize today's lecture. We began by looking at the reactivity of these transition metal alkyne complexes, and let me summarize this today's lecture. To begin with, we started by looking at the reactivity of transition metal alkyne complexes. We started by looking at cyclomerization reactions of various kinds of alkynes in presence of nickel and cobalt system, whereby we generated 5-6 membered systems. Now, these cyclization reactions of different alkynes slightly different from the oligomerization reactions or that we had studied trimerization reactions or tetramerization reactions of same alkyne, but today what we focused on was cyclization between 2 different kinds of alkyne. Some of the cyclizations, the cyclo-oligomerization reaction involved insertion of carbon monoxides as well as with that of the nitriles. The one with the nitriles resulted in the formation of heterocycles like pyridines, which is a value added chemical by this, and we have also looked at a number of such reactions. One could cyclize acetylenes. We end this discussion with Pauson-Khand reaction, where similar 2 plus 2 plus 1 cycloaddition has been achieved with an alkene, alkyne and carbon monoxide in presence of cobalt catalyst to give this cyclopentanone derivatives. Now, what is coming out through this discussion is the fact that transition metal alkyne complexes are extremely rich in terms of the reactivity that they show, particularly with respect to formations of various kinds of rings which are homocyclic, as well as cyclopentanones or cyclohexanone derivatives. In one case with iron carbonyl, we saw the reaction of acetylene with iron carbonyl gave rise to various kinds of products depending on the substituents on the alkynes. We have also seen that these iron being part of the cyclopentene ring as a metallocycle that can also be formed by reaction with acetylene with iron carbonyl compounds. So, this sort of further corroborates the fact that transition metal acetylene alkyne complexes are extremely important, particularly with regard to the reactivity they show, and this is somewhat different or probably very interesting as compared to other transition metal organometallic compounds that we have discussed so far, where the extent or depth of reactivity which we had observed for transition metal alkyl complexes are not that much for other classes of compounds. So, from that standpoint, transition metal alkyne complexes are of significant interest. So, with that I would like to conclude this lecture on transition metal alkyne complexes, and with that we come to end of this course on transition metal organometallic chemistry from principles to applications. We have but one lecture left. In the next and the last lecture, I am going to summarize all the topics that I have covered so far from the first week to the 59th week on this course, and we are going to have a walk down the memory lane in terms of the topics covered as well as the important points that I have stressed while we made this journey through the various facets of transition metal organometallic chemistry. I thank you for patiently being with me and listening to all these talks over these 59 lectures that we have covered so far, and I look forward to being with you in the last the 60th lecture, which will summarize all the topics that we have covered so far. Till then, goodbye and thank you.